inference and Bayesian inference, and what, if anything, do you learn from reconstructed jet measurements? Hopefully by the end of the talk, you'll have an answer.
Thank you. So okay, as Peter said, I'm going to try and kind of answer this question, thinking about what can jets add to kind of our Bayesian inference measurements. This may be a little bit familiar to some of you, but hopefully we can go into a little bit more detail and learn some things as we go along.
I'm sorry.
Yeah, we're good?
Kind of. Well, that's like.
Okay, we're good.
Okay.
It's almost so I can't actually.
We're good for the time being anyway.
Okay, then you can also like okay.
Pay no attention to the man behind the curtain.
Very good. Okay, I'll start with my traditional Bayesian inference introduction here, asking the question, right? Basically, how can we think about these jet quenching measurements, right? So we've collected a huge collection from RHIC and LHC in the last 10 plus years. This is really just a tiny selection of kind of inclusive hadron jet measurements. So there's a tremendous wealth of information, but we can ask the question, right? How do we actually systematically make sense of this? And of course, for today, my answer to this is going to be Bayesian inference. And so I kind of want to think about this in the context of 4 questions. So one, how do we take that picture, that all that information contained in those observables? How do we make it kind of a consistent picture from all of that? If we can make a consistent picture, what can we actually extract in terms of our physics? We can think of kind of what information is contained by different observables, kind of what is useful to measure, and then thinking a little bit about going into the future and some topics to kind of think about. So in terms of how do we actually do this, this will look familiar if you saw my talk last month at Hard Probes, but I still want to go through it here because I want to really give kind of a clear picture of how do we use these Bayesian inference analyses to try and answer these questions, right? So fundamentally, the question is, if I give you some model, I can try and ask the question, which my parameters theta, whichever these could be, is most consistent with whatever experimental observables I've looked at, right? This is all kind of described by whatever data X we have, right? And to try and answer this question, we can use Bayes' theorem, right, with kind of our 3 terms that we want to highlight. So on the right, we have our prior distribution, right, which is really just a way of kind of encoding very explicitly whatever our assumptions are about what our parameter assumptions are for the model. We have our likelihood, right, which really is kind of an all-encompassing term that's going to basically describe how well I can describe my data for any particular value of my parameters, right? So this can depend on things like the covariance between uncertainties, how those uncertainties are related together, both when we kind of think about this from an experimental perspective, as well as from kind of a theory side, if we're able to include those. And if we combine these together and compute in the appropriate way, we end up with our posterior distribution, orange on the left, right? This is really what we kind of want to, we really want to extract, right? This is going to give us basically to be very explicit, our most probable value of this then, right, is kind of our best description of the data. Then depending on kind of the shape of this, you might have to sample this to get a full description of kind of what your constraints are. But kind of bottom line is that this posterior distribution, if we can extract it, kind of encodes all the information that we really want to try and learn. So we've got our kind of Bayesian analysis piece. And so, right, if we do this, kind of systematically, all the way I'll go through in this talk, right, we can try and, kind of do the main question, for example, extract some transport coefficient. Right, but we can also do other things with this, right? We can really try and ask kind of broader questions beyond just what parameters I can extract, but really kind of can I really broadly describe regions of consistency and tension? Can I, for example, pinpoint areas of model improvement, as well as start asking questions? Can I turn this around and ask, for example, what new observables might be most sensitive to, kind of the model description that I have, and maybe able to provide us more information. So to say this kind of simplified and on the order of 2 steps, let's say, the concept here is that I'm going to try and create I'm going to take some model, create some sort of parameterization with it, right, which is just some way that some set of parameters that I can control to vary the behavior of my model. And then I'm going to try and explore this parameter space in some specified way. So I just take one plot from, one of our older JETSCAPE papers. It doesn't matter necessarily what these parameters A and C are. This doesn't necessarily have to be uniformly distributed in space, but the point is I need to be able to somehow systematically kind of explore the space in a way that I can then reliably determine kind of whatever my model predictions are throughout this overall phase space. Computationally, this is super expensive, and I'm going to gloss over pretty much all the details for how we do this. But basically, kind of the bottom line is we're talking on the order of kind of tens of millions of core hours to do these type of computations, and we want to employ all kinds of cost-efficient tools to be able to actually do this in a kind of reasonable, if expensive way, right? Actually, still make it tractable. Yeah, this can be in the form of machine learning. I'll highlight one particular example here. This can be in terms of kind of other computational tools to try and kind of reduce costs or compute more effectively. This is a huge topic I will only touch on. But the bottom line, what I want to highlight here, as we go in this direction of trying to look at, for example, our model, I want you to keep in mind that these choices that we make around our model, our parameterization, all of these things actually really matter. And so I can go through and I can choose my favorite model. I list a bunch here, but it's not comprehensive, right? You can choose whatever you want. For today, I'm going to use JETSCAPE with matter plus LBT, and I'll say a little bit more about this in a moment. This is one particular choice. You can, of course, choose your own. And these choices, they do matter, although I will at least talk a little bit about kind of what we see, and there may be some ways that we can kind of think about these conclusions more generally than just what you might pick from one particular model. So how are you going to go about doing this? You can do it in kind of different ways. In our particular choice for today, we're going to parameterize this jet transport coefficient Q hat, right, which is just telling you kind of how much transverse momentum you pick up as your parton propagates through the medium. So, okay, we have our analysis, we have our model, we need a third component, which is our data, and basically the overall point is I need some way to kind of organize what I want. If I just do my Bayesian analysis and I throw all my data at the wall, I will get something. It may or may not be consistent. It may or may not be interpretable. I don't know what to make of it. So we have some particular choices here. Everyone can make their own and group however you want. This one we organized from an example from kind of an experimental observables group.
What does your color code mean?
Roughly different classes of observables. I mean,
so things of a light color you group together.
So, yeah, something like
And
this.
that's in sensitivity space or something.
Perhaps, ideally, let's say. I mean, really, when we did this exercise to create this, we asked 10 people and got 12 different opinions. So, right, you can always make a different choice about how you want to do this. This is, the point is it just needs to be an organizing principle. So in this case, we kind of said each line adds some experimental element, and then we tried to kind of class observables in a way that we thought made sense. You could choose your own if you like. But the point is, it doesn't really matter necessarily what organizational principle you choose, except to say that what data you include does matter. So, right, we think really the strong way to go here is the goal should be include all observables that kind of are in a particular class. So if I say, I want to include my hadrons, my single hadrons, and my single inclusive jets, you need to include all of them, right? You don't want to try and kind of bias your extraction by some, for example, experimental bias. You want to try and be as inclusive as possible and let kind of these Bayesian inference studies kind of guide your question here. That being said, there certainly still is space for kind of picking and choosing. You can try and look more differentially, just for example, which you'll see, I'll go through later, right? Once you've done your kind of overall extraction, you then can kind of look more differentially at different selections of data to try and pick out kind of where your features are coming from, what's driving the behavior that you kind of extract. Right, so in terms of kind of what choices you make, okay, maybe I won't make this point again, but the point is the sensitivity is not always obvious for what observables might be best. And the way that you treat your uncertainties is very important here, although I will gloss over it for today for the sake of time. So I said lots of words. Let's just recap for a moment. What is if you absorb nothing else from that, all you need to remember is that we have our model, we have our data, we combine these together in some appropriate manner in our analysis. And this really gives us this approach gives us a rigorous data model comparison that really can tell us in a very broad general sense what is, kind of for a model, what is my best description. And then by doing this, you can then kind of iterate this in cycles and ask questions about kind of how can I, improve my model, how can I improve my data selections to, kind of spiral in towards a consistent description. So just in a word, I'm going to cover a very particular thing, and I'm really focusing particularly on this Bayesian analysis that we just posted on the archive. There is a tremendous amount of work on Bayesian inference in heavy ions, in the soft sector, in the hard sector, in heavy flavor, all kinds of things. It's great. I'm not going to talk about any of it today. So, okay, with all that set up, right, I really want to focus on this new paper we just posted, 2 months ago now, looking at inclusive hadrons and jets. So, we had a first generation of this where we looked at just a small selection of inclusive hadrons, kind of provided a proof of principle trying to extract this Q hat. Now, we want to do this in a more comprehensive way. We want to try and ask the question, what are inclusive jets bring us? And again, highlighting this point, we really want to try and be as experimental measurement agnostic as possible, right? So we really have taken all available inclusive hadron jet measurements, save one for a technical reason, and this basically gives us, in the end, effectively 729 data points that we're trying to calibrate our model against.
But you only use RHIC data at the top energy, not the 63 jet or.
That is a good point. We did only use top RHIC energy. I think that JETSCAPE's performance at 63 jet is probably quite marginal. So I think that may be that'd be the strongest argument for excluding that. So you want to be as inclusive as you can, but also you don't want to go so far into a region of your model that you also just know that you don't have a chance to describe. Nonetheless, that is a good point. Peter has a comment.
So Spencer, also look at the last column, PT range.
Yeah, that's the other thing.
And you'll notice it starts at 9 GeV.
Okay.
And both the star and Phoenix data, which I know very well, very many late nights working on the star data, that's only a very small subset of the actual published data, even for these data sets.
Mm-hmm. And this is another consequence of this is another consequence of precisely this point that we don't want to predict down to extremely low PT because we know that the model description is just going to be so poor, it's uncontrolled, and our theoretical uncertainties are so large. Trying to calibrate on that range is not going to give us meaningful calibration.
I think put it a different way, we actually don't know what the theoretical uncertainties are down there. Not that we're super confident. In this range, we had extensive discussions within the collaboration. Some theorists were pushing, strongly against lowering this 9 GeV, and eventually we just said, okay, we go with this. But indeed, it is not all, what one might consider to be, inclusive hadron suppression data. Right? It's a subset. So there we did make a choice.
That's a good point.
You're not afraid that introduces bias somehow.
It certainly does.
So it does, and in fact, we can see, for example, that basically if you look at, for example, a RHIC only calibration, the constraints are just quite weak, which is effectively a function of uncertainties get large at high PT. I will say something more about this later.
So just to complete thought, there's room for S Phoenix and for Star to improve the data set substantially in this sector.
Yeah. So I'm going to keep going back. I'm going to go back through my ingredients now in the opposite direction here in terms of kind of our particular analysis. So this will be my model, my equations heavy slide here. But basically, just to say a little bit about this JETSCAPE approach, we're using this particular choice of Q hat as this particular choice of parameterization. We are, you could certainly come up with your own, but this is the one that we'll use for the exercise today. Running through with matter plus LBT, so meaning that we have some transition value, this Q switch, where we switch from kind of matter at this high virtuality phase to LBT at this low virtuality phase. The feature that you want to keep in mind here is basically we have this hard thermal loop Q hat, kind of a more standard expression here, which we then multiply by this kind of virtuality dependent term. And really what this means is that you want to compare kind of the dashed versus the solid curves here. And really what this means effectively is that when we go to the high virtuality region, I'm going to reduce the number of interactions that I have there, which is going to induce kind of less quenching of these high virtualities.
So what is f of q squared?
So it's this expression here. It's some. It really is just. You can just treat it as some kind of broad possible description of kind of what this dependence could look like. You could choose a different functional dependence. We don't show this here, but we also kind of try to explore this a little bit. Kind of informally, there is kind of some hope of trying to do some sort of QGP PDF type description if we had some sensitivity to see if this could be some sort of description of kind of some internal structure. What we find is that we're entirely insensitive to kind of what the particular values of this term is. So you can kind of choose your the way that you want to take advantage of kind of the parameters that you have. This was kind of our particular choice that we used as a model to kind of run through our kind of not demonstrate, but rather explore kind of the machinery and how we can look at this kind of more differentially. I don't know if that necessarily answers what you're trying to get at, but helpful. Yeah. So the bottom line in the end basically is we have these 6 kind of total parameters, these 3 C parameters that kind of just give you some overall exponential shape here. We have some alpha S type coupling term between our parton and kind of the medium scale. We have our switch and then our start time for our quenching. We're going to run our partons through some calibrated 2+1 dihydro, and basically using this JETSCAPE model published in the last couple of years.
Actually, Raymond, if I could add a comment on this F function. So in the world of substructure, people talk about coherent or incoherent interactions. So there's some critical angle whereby if the jet splitting is sufficiently larger,
Click back so we can see that.
Sure.
is sufficiently large, then there's some incoherent interaction of the shower. Whereas for small opening angles, it's coherent. It's kind of a quantum mechanical, coherence effect, a little fuzzy conceptually perhaps, but that's in jet substructure. There's that kind of discussion. This is similar motivation, but it's now a continuous function of jet virtuality as opposed to talking about a specific splitting within substructure. So all of these are trying to get at how does a jet interact with matter, and if the virtuality is sufficiently high, it's not a broadly distributed shower where you've got individual components. It's just some blob that interacts less with the plasma. So that's going to try to parameterize that with some theoretical reasoning behind it.
Why is X in there?
X. What's X?
X. Okay. I assume that's Burkane X.
Yeah, it is. So it's related as I probably should replace that expression, but it's related basically to the energy and temperature in the medium. Why it should be precisely, I would say that the overall form of this kind of expression is somewhat arbitrary. It was a choice, but it really is. We also looked at, say, kind of a more kind of binomial form. It was just to see kind of what general functional shapes we're potentially sensitive to. As I said, we'll get to in a moment, is basically we are, at least on the inclusive hadron and jet level, we're pretty much entirely insensitive to what the shape of this function looks like. So, to highlight the point, this is really one particular model choice. You, of course, want to try and do this in kind of a comprehensive manner where you're in control of your various pieces of your model and can vary kind of choices like this and see what impact that has. So we've got our data, we've got our model. I want to highlight one particular point on the analysis, although there's many things that you can talk about here. One particular kind of new addition that we've had here is an implementation of active learning. So if you think back to my picture before where I showed you this A and C and you're trying to explore your kind of overall phase space, I need to run my model at some particular set of points there, and then I'll use some computational techniques to allow me to kind of, using these so-called Gaussian process emulators to allow me to not have to run at every individual point. But you can ask the question of how do I actually decide what points I should run my model at these kind of high statistics, very expensive computational runs. And so the conventional answer is to just start with a Latin hypercube to just basically stay still my points for some set. But what we introduced here was an approach kind of where we iteratively decide what points we want to choose based on points that we are most uncertain in our phase space about kind of what their actual values are. So kind of conceptually what this means is that if I look at kind of my uncertainty as a function of one of my parameters, right? You can imagine that if I select points, for example, here, here, and here, right, I'm well constrained here, but as I move away from those points, I have larger uncertainties. So the concept is we run kind of in batches, and as in each batch, I identify these highest points, run my simulations at those, and then for my second iteration, for example, I end up with my kind of red curve, right? So basically what I'm doing is I'm going to kind of systematically knock down my uncertainties on my emulation, basically as long as my computing budget allows, or until happy, if you will. So the point here is that this is really just a kind of model question. You don't want to look at your experimental measurements because you'll bias kind of what your calibration will look at that point. But this is a new approach that we've kind of introduced here to allow us to kind of improve the size of our, basically effectively our simulation uncertainties at a lower computational cost.
And you evaluate the uncertainties by what, some sort of a gradient?
So in this case, where we kind of do so a Gaussian process can basically, if you train it on some set of points, you can ask it what the uncertainty is off that point. So it's basically just a value I can extract out of my model, and so that's what this represents here.
So, sorry, a question, and if it's a long answer, then don't worry about it.
Sure.
Now, but it's very clear in the one-dimensional case how you do this choosing of this. Is there a simple way to describe how you deal with that in a multi-dimensional parameter space?
So I mean, yeah, conceptually it's exactly the same. I can just ask my Gaussian process kind of what my uncertainties are as I move to any particular point. So I can just scan my phase space then and kind of ask for that. There is the details of it are a little bit more complicated than that, and there's actually some kind of space filling components in this to make sure we don't just end up stuck in corners of phase space. And there are some further details, but I would point you to the paper for that.
That's perfect for that.
Maybe again, if this has got a short answer. But are there assumptions here about how much the model predictions change as you change the variables? I mean, if you had something where you expect spikes, you'd have something different from broad curves.
Yes, absolutely. So
That's the art of it.
yeah, so implicit in this, generally speaking, is that we did some kind of broad explorations of at least the underlying parameter dependence, and we don't see it's generally smooth. If this really had you had some kind of very high frequency structure, you were very sensitive to particular parameters, you would get in trouble taking an approach like this. So that is definitely implicit in this work.
I think at some point you have to bring in physics intuition. Do I expect my predictions to vary rapidly in model space? Do I expect high frequency just from the physics of the model?
Correct.
And so, but let me also point out you can also use closure tests whereby you use the Gaussian process, result emulator to emulate a point at which you've explicitly calculated and see whether you get a consistent result. And so you can do tests like that.
Yeah, which are generally things that we do when we're training our Gaussian processes and things like this. But for the sake of time, I'm already half an hour in. We tend not to I didn't want to go too much detail here. So, okay, thanks for hanging in. We've got all our model components. We've got our analysis, we've got our data, we've got our model. We can actually take a look at what we're doing here, right? So I just show you a small selection of our data here. So on the top, right, I'm going to basically show kind of subset of my prior calculations in the blue compared to my data in the red. I perform my Bayesian analysis, following all the details that I just talked about, all the checks we do. And basically what I get here then is on the bottom, I have my data compared to my posterior distribution here. So the width of this blue is basically representative of kind of the width of our posterior distribution. So to say a little bit more, here is kind of the overall comparison between our inclusive hadron and jet data and our posterior. You really don't have to squint. I just want to show it here because I think it's it's a very nice representation of kind of what we've done. Bottom line, overall, it's described fairly well. there are some regions of tension which we can go through. So first we can start with kind of our hadron RAA at low PT. So here we're looking at Ehlers, star, and Phoenix, and very much to, for example, Spencer's point, right? You can see the restriction on the RHIC data here, which definitely is going to limit the impact that it has in the calibration. But broadly speaking, at low PT it does quite well as a function of kind of our centrality here. But now if I look at, for example, high PT, I showed just a selection from CMS, and we start to see quite some meaningful tension in this high PT region, right? And how you can think about this already is that basically, if I think about my experimental uncertainties, my hadron RAA at low PT is going to be my most precise. My Bayesian analysis is going to take these uncertainties from the experiment seriously. And so if I do that, right, I really have kind of my most constraining points at this low PT. And whatever's happening at high PT, even if I miss some, I'm not penalized as much. So we'll explore this more as we kind of go forward. We can also, though, look at our jets, try and start thinking about what are our jets bringing this combined calibration. And I show a selection here from Ehlers, Alice, and CMS. And kind of the broad story is that it's generally in good agreement. I can squint at this a while and we can try and dissect it, but generally does fairly well with our jet RAA. So then we can go from kind of the comparisons that are shown you in the data with our calibrated posterior. I can then try and turn it around and get back to my parameters. Immediately, I'm going to try and narrow this down a little bit. These C1, C2 parameters that are in our FFQ squared function that we talked about earlier, they're really just entirely unconstrained. So I'm just going to skip these for now. So then what we're going to do here is we're going to look at two calibrations. So one is our combined, so doing hadron plus jet, what I was just showing you in the comparisons. That's in our blue here. And then I'm also going to show you our hadron only, so we can kind of try and look at a question then of how much difference, for example, is the calibration, including and excluding jets. And so we can go through our different parameters here. We see kind of a fairly high value, this alpha S, fairly consistent between our two calibrations. These dashes are just for illustration. They're not extracted from the distributions. We see a fairly late switchover from matter plus LBT, kind of in the order of 2 GeV or so, which is also consistent with kind of our last calibration. This quench time, we see start to see some differences between kind of our hadron and jet behaviors, broadening kind of this distribution when we include our jets. Then the one kind of parameter we do see some constraints on is this last C3 parameter, which is kind of in our normalization for this FFQ squared term. So if you go back and squint at this for a while, basically what you'll come out of this is that it needs some reduction at this high virtuality kind of range, but which is I think pretty consistent already what we've seen even before Bayesian analyses of this, but kind of the exact structure of this or the exact value even is quite broad. Okay, so we've got our parameters, and then we can kind of put all these pieces together and go back to our Q-hat extraction, which is what we see on the right here. We kind of made a particular choice here, which I'll get to in a moment, to plot just this Q-hat HTL term in our Q-hat, and you may ask, okay, why are we doing this? And to answer that, I'm actually going to go back to a very nice review paper from a few years ago now, where you see kind of this whole extraction of Q-hat over T cubed, a traditional way of plotting this, from quite a nice variety of analyses. You see we have this very broad range of extractions. And at first glance, you can put, it's nice to look at this, and you can put them all on a plot, but this is kind of glossing over some very important details. And it's really glossing over the fact that all these comparisons may not actually be the same, right? Some of these, for example, are quark versus gluon extractions, whereas traditionally we plot kind of our quark values here. And so, in fact, even if I want to compare to the previous JETSCAPE calibration, I need to make sure that I'm really doing an apples-to-apples comparison, which in this case means that instead of reporting this FFQ squared term basically being equivalent to 1, I need to instead evaluate it at some kind of mean virtuality that was used for the last analysis. And when I do this, then what that's going to do is that's going to shift my overall curves down. That now kind of puts us in a place that's consistent, for example, example, with the previous calibration, as well as these so-called jet collaboration points extracted kind of in a more separate analysis. So now, of course, though, because we're quite uncertain in again this kind of dependence of this FT squared, we kind of our uncertainties correspondingly increase. We are, the point is we're not sensitive to those particular choices. So, right, I will come back to this a little bit later, but the point is this really highlights another way, and the importance of making consistent comparisons. So we were able to do this here, but even just kind of if you look at each different measurement, trying to make those comparisons directly can be quite difficult. So, okay, so what's next? So I've shown you kind of this first calibration, great. But what can we do with this? I want to really kind of demonstrate by looking very differentially, what information we can extract from including these jet measurements. I want to think a little bit of kind of what information is contained in each observable, what observables are promising to take a look at. So the first way we can do this is just by doing kind of a simple breakdown. I'm going to do one calibration with my jet-only data, this is in the blue, and one calibration with my hadron-only in this kind of orangey yellow color. And already we see quite striking behavior. In fact, there starts to kind of be some sort of separation in the dependence that we prefer, that the model prefers from these two cases. So we can project this down to 1D just to make it easier to kind of look at the distributions. And again, you can see kind of quite strikingly, there is some region of consistency between them, but the peaks of these distributions are certainly quite shifted between the two.
Do the hadrons dominate because they have better statistics?
Yeah, so partially, that's part of it. It's also just a question of kind of relative number of data points between your hadrons and your jets. So you can't do a simple kind of reweighting between these two distributions to get the combined. But yes, in this case, it seems to be dominated. The combined is quite dominated by the low PQE hadron, with small uncertainties. Oh yeah, sorry.
Why hadron will not give you the higher Q hat than the jet? Why the hadron data prefer the higher Q hat than the jet data?
This is a very good question. Let me come back to this in just a moment, please. I think I at least can say a little bit more about it. So we can try and ask the question, basically, can we disentangle why the jets and hadrons are showing this behavior? Is it really something kind of inherent about difference in observables, or is there something else that can correlate with it? So one direction we looked, for example, is centrality dependence, right? You have different median properties, and for example, 0 to 10 versus 20 to 50, or kind of more semi-central. And what we see here is, we still see this kind of split in our behavior.
What's the red and the gray?
So the red, the top value here is the combined calibration. The blue is the jet only, and the hadron the hadron only is the yellow. So basically, you still see this kind of same sort of separation where my combined calibration kind of matches both, but then I see the separation going into different.
And what you showed us before is more equivalent to the right-hand picture.
I mean, they're okay. Maybe it's a little hard to see, but I would say that they're quite similar. It's just this is 0 to 10%, this is 20 to 50%.
It's a complicated weighted average. You would kind of draw the jets seem to pull the combined more in the central than in the non-central. This may likewise be kind of relative size of data sets and uncertainties. So there's all kinds of pieces that go into it.
Yeah. So, right, okay, we split by jets, centrality doesn't seem to work. You could ask, is it really kind of a function of precisely jets versus hadrons? Can there be some kind of other hidden source? Is Q hat even necessarily expected to be kind of consistent across these different observables? Or is there perhaps some kind of observable dependent contribution to Q hat? But the last approach we'll look at here is whether there's kind of a confounding variable here, namely kinematics, right? So our hadrons are going to be covering a lower kinematic range than our jets. And so what we can do here is we can try and do a breakdown as a function of basically jet PT or hadron PT. And so, right, I've already shown you this, kind of highlighting this point. We see this tension at high PT. We've already seen this plot before. But we can then play this game and we can start selecting by varying our minimum hadron PT, right? And so if we just focus here for a moment, if I go to kind of high PT hadrons, which these are basically going to be hadrons that are dominated by our jets, we see now that this high PT, it seems to really do quite well. And okay, if I did a chi by I might in fact say that this kind of better describes all my data, which highlights the importance both of taking kind of our uncertainties seriously from a Bayesian perspective, but also the importance of doing that beyond just kind of a chi by calibration.
What do you mean by hadrons large? The two curves have the same range, so where is the low?
So right. So what I'm saying. So yeah, right. So what we've done in this bottom plot is for the calibration,
yes.
I only fit on this side, so only above 30 GeV.
Okay.
But then I can still ask the question of what okay.
But I mean, that's what you would expect, right? Because if you take everything, you're dominated by the high statistics, which is low PT. And if you throw them out, then you're gonna fit the high PT stuff better.
Of course.
Right. So I mean, right. So this certainly is expected that right. If you only calibrate in this range, you expect to do better. But what I want to then do is take that and look back at my Q hat calibration, right? And what I see here then is that really, if I kind of interpolate my selections on my PT, right, this makes it very explicit. So, right, my hadron only is kind of to the right, dominated by my low PT data. And as I raise this up, I become more and more consistent with our gens, right? So really, what this is saying is that if I, basically, if I'm my high PT hadrons are consistent with the picture that I expect from my jets. And it's really that this low PT hadrons are kind of dominating our picture. So to say the same words here, right, this is really kind of, we can turn this around and say this actually is really pointing to a region of phase space for improvement. So if we can, right, if we're kind of extracting a consistent calibration here, but now starting to see tension as we go low PT, this is really indicating to us that somehow our description at low PT from our model is maybe not as great. So there are questions you can ask here about what theory uncertainties you want to try and include. This is using a leading order Q hat. In this particular case, it doesn't have shadowing. We also we have a cutoff once you get to below kind of this protonic phase. Your energy loss cuts off immediately, which isn't exactly a physical assumption. Excuse me. So. Right.
Is this Q hat, is it temperature dependent?
Which?
Or is it just a number?
Sorry.
So you have Q hat over TQ, but is Q hat a number or is there a temperature dependence?
So, I mean, we extract a Q hat that's a function of energy, temperature, and virtuality. But in this case, I'm plotting at fixed energy and temperature for the purposes. So then, yeah, this width is really indicative of kind of our calibration. And so the thing to take away from this is that we have a little bit of a tension here, right? And that our smallest experimental uncertainties at our lowest hadron PT is the region that we seem to have kind of the largest theoretical uncertainties, right? So really having a way to systematically and carefully account for these theory uncertainties is something that's definitely needed as we go forward. Trying to make sure I have the time. Okay, so I want to look briefly then at kind of a next study that we've done here, right? So if you remember my taxonomy from before, right, you can choose whatever observables you're excited about. In this case, we wanted to ask a question about jet substructure. We did this in a kind of very simplified manner, focusing on a selection of data with some simplifications in our uncertainty treatment. The bottom line, this is really more of a kind of exploratory study, but we want to take a look at asking the question of, if I now add these new observables, can I actually change my calibration? Can I improve my calibration? Can I get something consistent? Is there actually additional information, for example, that these substructure observables carry that's not just in the kind of overall spectra? So we use we're going to do a calibration here using just the jet RAA only versus doing the RAA plus the substructure observables that were available at that time, which I'll make a note that because of how we run this, we're actually doing a recalibration or reanalysis now effectively. So all of the substructure observables that have been measured in the last 2 years, and there's been a huge collection of them, are eminently coming for this type of analysis. So, okay, lots of words there to say, but basically, there's two things that you should take away from this. So one, my jet array is in blue, so I've gone from my prior distribution to my posterior. I have a significant constraint, and I see that if I compare it to my including the substructure, I see some actual meaningful. Okay, I didn't have the animation there. I see some meaningful constraint on these values, and they're consistent in how they're extracted. Yeah, there's some caveats on kind of the overall scale here. We can talk about it another time, but the bottom line is we seem to actually have an indication that in this analysis we are really these additional observables carry some further information. Now, you should of course keep the analysis that I just showed you in mind as you think about this, right? Because this is really quite interesting. Because now we see that where I had my tension between my inclusive hadrons and jets, right? If I then look at it in a substructure observable, which has some sensitivity to these low PT hadrons, about the same hadron PT range, in fact, we end up with a consistent calibration. So this is still something that we're trying to think about further and investigate. But I anticipate that, by the time we get to the end of this, we'll have again, kind of a nice ability to look at this quite differentially, like we've done for the inclusive hadron and jet study.
So,
Yeah.
right corner part, so the Q hat structure from jet only is more reliable than the combined result. I
don't know if I necessarily would say more reliable. I think it's I think the fact that okay, again, if you stood.
No trustable, you have theoretical uncertainty, you cannot be trusted.
So, perhaps.
Can you tell us what the theoretical uncertainties are?
That's the problem,
That's
right?
the problem.
Right.
Yeah.
So, what I said there. I think I stand by. I think that there are larger theoretical uncertainties as we go to lower hadron PT, but I don't know precisely what they are. And it may turn out that that's
Jet observer, you can control your theoretical uncertainty.
Perhaps. But we're also just at a higher PT, right? Because we can't measure. Now we can graph, but until recently, it was very difficult to go to quite low PT, right? So you're kind of sticking more in a perturbative regime, right? So I don't know if I'm quite ready to say one is better than the other. And in fact, if you look at some other kind of calibrations, for example, using hadron only, you in fact see that you can get quite some precise calibrations depending on what data sets you include. So I think it's bottom line. I think it's worth thinking about whether we can kind of answer these questions, but I don't think we're quite at the point where we can say we should focus on one over the other.
Then you also have, additional physics going on in the low PT hadrons. You have multiple interactions, you have medium response, so it's just plain old more complicated.
Right, I agree, and I think that's exactly kind of, I guess what we're trying to get at a little bit in terms of our kind of theoretical uncertainties, or how do you actually account for that? Because our model, doesn't have some of these factors, right? So can you account for this in a systematic way?
Your model probably does, so matter plus LBT has a lot of stuff in it.
It does,
but your simple functional form does not.
So the parameterization, this is a good point. The overall kind of shape of this kind of overall curve is dictated by the model, not by the parameterization. The parameterization can give you some more or less flexibility in terms of kind of what overall shape you can have. So, you're not going to end up with, it's easy to point this kind of on the Q hat plots, but the fact that kind of the model doesn't rise high enough here is really a feature of the model, not of, for example, the FT squared.
In both cases, the model is flatter than the data, both in the blue and the yellow.
Right.
Barbara, we speak about Q hat as a transport property of the quark-gluon plasma. I've said those words. You may also have said those words. If it's a transport coefficient of the quark-gluon plasma, that is kind of a universal kind of quantity. It's a property of the medium, and you should get the same answer if you probe it in different ways. We are not getting the same answer if we probe it in different ways.
But I think that your low PT hadrons have other things going on too.
So that
They
makes
have
sense.
some non-equilibrium interactions with each other. And you have a medium response, which is also non-equilibrium.
I'm not disagreeing with anything you said, but if a formulation purports to extract a transport coefficient of the quark-gluon plasma, you take it at face value, if I may, rephrase what you're saying.
You're saying the model should reproduce the data anyway, if it has all that stuff.
If the model is correct, you'll get a consistent answer. Evidently, the model is not. I think we're saying the same thing in different words. But I think it's precise to, once you be very clear about what you're trying to do and what's been accomplished. So this model is inadequate. We agree with that, but we have a tool to actually expose that and identify a correct model when it comes.
Yeah. So, okay, with just a few minutes left, I want to say just a little bit about what's next. And so I want to say just a little bit about kind of different model comparisons. So I have a very, very biased selection of observables here. They all just happen to be measurements that are made in this group. But
not all the measurements that are
not all of
in this
them.
group either.
Just a very small
Subset.
selection. Indeed. Right, but the point that I want to make here is there's too much information to kind of stare at this easily, but the underlying point is that we have a huge selection of models, and on some observables they do very well at describing kind of a particular dependence. But kind of systematically across, if you look across observables, you start to see tension pretty consistently, I would argue. So how can you confront this? Well, you want to be able to kind of do a calibration, but important in this is that you need to be able to do it in a way that's really apples to apples, right? If I change not just kind of my energy loss module, but really every other piece of my calibration, I run through different hydro, calibrated somewhat differently, all these other details, it becomes very difficult to kind of try and do this in a systematic way. So, I think what I've shown you so far is that when you can really look differentially in a particular set of models, in a particular fixed environment, you can try and pull out quite a bit of information. You can extract quite a bit. So I think really the bottom line here is that it's very important to be able to kind of calibrate with multiple models in this way. I can take off my JETSCAPE hat for a moment and say, as a practitioner in Bayesian analysis, I'm happy to do this any way we can, but I think it's critical to be able to go do this going forward. To Barbara's point, then, so I think I emphasized significantly as I was going through that the details matter, right? We can try and extract these calibrations, and this is all very good. We've already seen what we can do, but we also can try and do better in how we're trying to do these analyses. So one thing you can think about is, for example, how do you actually parameterize Q-hat? What do you actually want to encode into this? And so I really, and unfortunately, don't really have time to say too much about this, but let me just say that from our kind of previous JETSCAPE Bayesian analysis, we had a fairly inflexible parameterization. So if I move kind of up in this range, it's going to systematically move up, which means, for example, my low PT influences my high PT. And that may not necessarily be a feature that you want, right? If I'm, for example, looking at RHIC, and I only kind of get up to some temperature value with my median, right? I don't want to then calibrate further beyond that, kind of based on my low PT data. So there are alternative approaches to doing this. So instead of using this HDL approach, you can use, for example, this information field from a number of our collaborators here, approach that really gives you kind of a broad flexibility. It's basically a class of functions that can describe your Q-hat, although in the process you kind of lose some physics interpretability. So you need to think about these questions very carefully. To say any more about this, I will point you to my hard probes talk where I talk about this and kind of an overview of kind of the state of Bayesian calibrations, the hard sector, beyond just kind of the analysis that I presented here. The other point that I want to just emphasize very briefly is the question of kind of uncertainty quantification. It's come up kind of again and again. How can we think about these theoretical uncertainties? I haven't even talked about experimental uncertainties, but I will use this moment to remind experimentalists, please report signed uncertainties. It's for whatever sources you can. You don't have to report the full covariance, but even the sign can give us enough to construct much more precise calibrations than if you just report a single number. So, okay, with that, there are basically, the way that we kind of perform these analyses, there's definitely room for improvement in terms of kind of new tools, new techniques. So in this case, I show kind of some excerpt from a study from collaborators in the so-called Bayesian Uncertainty Quantification project, where they're doing studies of different emulation techniques. So this Gaussian process that I mentioned, how do we kind of reduce the cost of our overall numerical simulations. And there's a ton of information here, but basically what I want you to walk away with is that for these type of closure tests, you want to kind of be consistently near around this zero value. And in general, this kind of new emulation technique that has a better sense of what the uncertainties are of the training data that it uses shows that you can actually kind of fairly consistently get a better calibration. So you can then kind of see this. So this is for looking at some observables. I can then look at kind of my parameter extraction, so similar to that corner plot that I showed you before. And basically what you'll see if you squint, okay, maybe I should clip this down, but in any case, if you compare, for example, this green one, which is kind of a more traditional one used in our calibrations, you can get a much better extraction by having a kind of an appreciation of these uncertainties. So
it's more precise, is it more accurate?
Yes, it is. So these lines here, sorry, this is too small, I should have clipped this, but the lines there are the actual value. And so it does in fact quite well in terms of.
Look at the right corner plot of the rays.
Down here?
Yeah.
Yeah, so okay, it does
Still better.
it does slightly worse, but I don't know, on a 25 or 20 parameter calibration, I think that does quite well.
But the red and blue are better than the green.
Yes. Yeah. So I'm unfortunately out of time here, but the bottom line is that these questions of how we think about this is, I think, really a very important thing, and it's important. We see certainly here, but then also, right, this Bayesian EQ project is looking at how we can kind of apply this across a variety of nuclear science topics. So this paper is from some Bayesian EQ collaborators, and there's, I think, much more that can be done here. So I'll come to one last question, which comes back to our first question, maybe about what can we do this, or namely where can RHIC contribute to this, or kind of more broadly, what do we want to measure next? And so we're still working on kind of full sensitivity studies. There are systematic ways to kind of do this, but I'll give you my speculation. So I think this high PT hadrons at RHIC, so from STAR as well as from S Phoenix, could go a long way to kind of increasing the ability of RHIC to influence these calibrations. And then I think continuing kind of on our journey for looking at high precision jet substructure, I think looks quite promising in terms of kind of what additional information it might carry. We'll have to continue to kind of do these studies and see how this looks as we include more observables. But this is at least where my attention is at the moment. And as we do our full sensitivity studies, we'll be able to do this in a much more systematic way. So, okay, with that, I will summarize very briefly here for the sake of time. But the bottom line here is, right, Bayesian inference. I showed you a very particular application today, but it really is kind of a broad, rigorous tool to make model data comparisons. And it's not just about kind of playing on a Q-hat, but really trying to do these systematic studies to understand what the dependence is. We have this new JETSCAPE calibration, including JET-RAA. I've shown you all these different kind of questions we can look at differentially. Some we show you here. Others we're kind of still in progress to really try and look fully schematically in terms of, for example, our substructure. But already you can see kind of we see these regions in the models that really need some kind of improvement as we go forward. There's a lot to be said for that I didn't get time for today, talking about kind of these cost-efficient tools and how we can think about uncertainty quantification. These are really very closely related, and really presents kind of a important direction for future calibrations. And then, the bottom line here, we have this nice calibration, but it's really important as we go forward, if we want to kind of generalize these conclusions, to try and do this in a with multiple model calibration. There are tools in Bayesian inference that really give you a very direct answer of what models give you the best description. So we can do this in a very kind of clear quantitative way, but we need to do it kind of appropriately together as we account for both our theory uncertainties as well as our signed experimental uncertainties. Thanks.
Questions from outside? Questions in the room?
Motion cost. Why not include flow data?
Sorry?
Why not include collective V2 of these three data in your constraint analysis?
You mean for high PT or low PT?
High VT.
So high PT is basically if you go back to our taxonomy, we kind of class this as the next set of observables. So there are some technical reasons why it kind of didn't make sense to include it here, but that's certainly there's a number of kind of next steps we're doing. So kind of underlying all this is we have a huge amount of simulations that we store in a manner that we have kind of everything on disk. And so we can do a reanalysis of the jet substructure. We can do look at our V2 observables. Anything kind of inclusive, we have an opportunity to kind of look at further, and this is what we're working on, as well as taking a look at, for example, some gamma triggered observables or Z triggered. So the answer is it's coming. All these things are coming. We're just not there yet.
So I'll ask you a completely predictable question. I'm sure you know what it is. Would energy correlators be useful for this?
So
It's
always
high precision.
Always more observables are useful. Certainly, I think high precision is interesting. So that certainly will be a nice piece. I think energy correlators are kind of an interesting question right now because there clearly seems to be some tension in kind of how models are describing the data or not. So I think certainly I would be very happy to see energy correlators show up and try and add them as the next step. Yes,
Let me ask Barbara a completely predictable question. What do energy correlators bring that's better or different than other observables? Is it a matter of experimental precision? Is it a matter of theoretical, accuracy? What's new in energy correlators whereby you might expect them to add to this?
Well, so the large RL region, which is the perturbative region, is pretty well described theoretically with perturbation theory for PP collisions. And a lot of the weird stuff that happens in lead-lead collisions, which presumably is an outcome of a finite largest Q hat, that actually modifies the energy correlators in precisely that region that's well understood theoretically without a medium. There are different models that calculate what the medium does there. So I think that half of the energy correlator spectrum is calculable and calculated in several different models.
And bottom line,
And I was just going to say you have the magnitude and you also have the slope with the opening angle. So I think you have some differential information that's you don't have as differential as say RAA.
In any case, what I can also point out, I hope the conclusion comes through here, right? We can ask the question, what do energy correlators bring to these calibrations, right? Maybe, we may see that it, for example, is quite discriminating, or we may see that, the information carried by, for example, our group substructure observables, recovers much of it. We have a way to ask that question.
Yeah, because it's hard to know a priori.
Right. And so, these sensitivity studies, right, you can also ask questions about kind of new observables, or imagine if that high PT hadron data from RHIC actually, existed with, small uncertainties, how would that actually impact calibration? So these are all kind of questions we can try and ask. It's all things we're interested in.
So looking back at this tension between the high PT and low PT or the hadron jet, so there are a lot of different ways you could try and address. So let's assume that you think it's an issue with the low PT modeling.
Right.
So there are a lot of different approaches you could take. You could weigh the data so you're not sampling that region as much, so it can't bias other areas. You could make crude models of the things you're missing to get an uncertainty, although you would then have the correlation in it. You could use the discrepancy to try and fit things, or you could just look at other models to see if they have that. So So it's good and bad that there are a lot of different ways you could go. Is it like in a case like this, is there, is there a way that you're thinking about doing to either understand better what the discrepancy is caused by, or change the model or the fit so that it doesn't bias things too much everywhere else?
Yeah, so my kind of gut feeling at the moment is that the best approach would be to try and change some of the model contributions at this point. So the ones that I highlighted, namely this kind of cutoff for Q hat below the kind of temperature. Basically, what it means is that it just goes to zero, which is kind of a non-physical effect, right? You'd expect some transition. This is something that I think is relatively straightforward to implement. Speaking out of a little beyond my expertise here, but as I understand, it's fairly straightforward to implement. So adding shadowing, and already trying to kind of take an early look, I think would be a good place to start, because these are kind of already things that we've identified that and it may be that there are bigger effects beyond that. So this question of whether you kind of reweight these things and to kind of de-emphasize this, we started thinking about these, and this is also the benefit of kind of something we can do now as opposed to rerunning some model calculations takes more time and computing. So I think in my mind those are kind of the directions I would go in terms of kind of trying to add those additions to the model. If it turns out that we need next to leading order Q hat, then this is very much some time out. So I think it's a balance of kind of what is accessible and possible. And if it turns out we strike out on kind of these more straightforward additions, then I think we need to think very carefully about how can we choose a kind of stable point at which we're kind of confident in our model effects, or if we can account for these theoretical uncertainties, that also gives us an out there. It may just be that our calibration in that region is weaker.
I mean, it's something in a simplified analysis. That's a kind of conventional approach. Put in models for these pieces, but of course, then every adjustment to the model is a lot of effort here.
Right.
Slightly different approach, although I suppose you could put in your best of everything. If it resolves all the discrepancies, you can spend the time to figure out which one actually mattered, or you can just be happy, I guess.
Right. No, you're asking the right question, though. It's something we're thinking about as we kind of go to the next round of calculations.
Okay, more questions? We're losing our audience here.